All right. Well, I literally have nobody here in person today, so this might be a little bit awkward, but I'm going to kind of have to rely on some of you who are on the Zoom. If there are specific problems you guys want to see me work through on either practice exam, kind of let me know what those would be. Otherwise, I can think about some general things that might kind of be some good tools going into the exam either today or tomorrow whenever you decide to take it. It is 20 questions, each worth kind of four points, and then the final short answer is worth kind of 20 total points. There's 4 different kind of parts there, each worth a couple different, each worth I think 4, 6, or 5 points, adding up to 20. Make sure you upload kind of a Word, an Excel, or kind of a photo of your work to get full credit. But also, if you get it wrong and you just give me the wrong answer, and I can't see any of your work, I can't really give you any partial credit. So make sure you upload as much of your work that you did so that I can give as much partial credit on those, okay? So, since there's nobody here, I'm gonna go. I also had someone that was using the room before me, so I was waiting as long as possible to boot them out. So let's go look at these practice exams. And if you have any specific questions, we'll kind of start with those. Otherwise, I'll try to just talk about some things in general here, okay? So I'm not seeing anything in the chat yet. Are there any specific problems that you guys want to see me work through? Or just generalized like questions about the exam or about a specific topic that will be on, likely be covered on the exam. Nobody? Okay. All right, well, I'll go through one thing here, I guess. So one thing that I guess I've kind of seen some questions on, I think I did this last week, but just a reminder, I would maybe suggest if you print out the formula sheet or you have the Word document, on kind of the blank space there, I would remember that anytime you're looking for critical values, and it doesn't matter if you're looking at a student T, right, or a standard normal, they're both going to be centered around 0, right? So anytime I have a right-tailed test, which as kind of a reminder, right-tailed test, I'll show you on the formula sheet how we can remember this as well. So if I go down here, anytime I see a greater than sign in my alternative hypothesis, I've got a greater than, or maybe one thing you could write this down to remember, a right-tailed test, or I find the p-value is what's in my right tail. Right? Less than sign in the alternative hypothesis, less than test, so my p-value is what's in the left tail, not equal to test, or a two-tailed test. That's when I find the area that's in one of my tails and multiply it by 2, right? Because I'll have 2 tails, so half the p-value will be in each tail. So if I'm looking for critical values, they're going to be, depending on whether or not I'm using the standard normal or the student T, it'll be a Z or a T value that gives me kind of alpha in this upper right tail for a right-tailed test. So for a right-tailed test, I know that my critical values that give me alpha in that right tail will have to be above 0 or positive. Right? Anytime I'm looking at a kind of left-tailed test, it's the critical value that gives me alpha in that lower left tail. So for a left-tailed test, I know my critical values will be negative. And for a two-tailed test, I'll have a pair of critical values where alpha is the total area of my tails. So alpha over 2 will be in each tail. Right? So if I'm thinking about there for a two-tailed test, I have a positive and negative critical value that gives me alpha over 2 kind of in each tail. So this will kind of help you or prevent you from making pretty easy mistakes. Just always knowing for a right-tailed test, critical values have to be positive. Left-tailed test, critical values always have to be negative. And for a two-tailed test, for any one level of alpha, you'll have a pair of critical values. Okay? So that'd be a good thing to kind of have written down prior to going into that exam. We'll go through the formula sheet Yeah, I can actually, I did this with someone earlier. I think this is probably a good use of time. Let me see. Okay. So if I'm thinking about, what's the best way to do this for you? I'll probably open up the Word document. That might be the best way to do this. Insert some text boxes. Okay. So once again, just a reminder, if you view this on the Canvas, this Word document will look messy. If you download it, it should show up to you pretty easily, or pretty nice. So let's go some text box here. Might be the easiest way to do this. Maybe not. So what do I want to do here? Oh, I know what I'll do. Okay, actually text. So these kind of groupings, these equations that we have right here, and you could write them on the left side or kind of on the right side. These are going to be all the uniform distribution problems. Right? So this kind of grouping of 4 here is your uniform distribution problems. All right? Up here is just kind of a reminder that the standard deviation is the square root of the variance. Right? That's all this is. So it's not, that's just kind of a reminder. Hopefully, we kind of have that burned into our mind at this point. The standard deviation is just the square root of the variance, where sigma and sigma squared are the population standard deviation and variance, and S squared are the sample standard deviation and sample variance. Okay. All right. So, why is it going to do that to me? I don't like that. Yeah, let me do this again. There we go. So we had our uniform distribution problems up here. I'm thinking about what these two equations are. There I'm going to have, you think about this as my normal distribution z-score. So this is when, I'm looking at a normally distributed variable. I already know I have a known population mean and I know the population standard deviation or variance. I'm not if I know the population mean, I don't have to do any type of hypothesis testing or confidence intervals. So this is just going to be simply the equation that I use, right? So this was like for the examples that we saw. Oh, come on. Clear this. Clear it, please. There we go. So this is going to be like what we saw on practice exam A and B when we're kind of just dealing with a normally distributed variable, like in 5 and 6 here. Okay. We then have kind of these equations here, which just remind us, here's the equation to find the standard deviation and the variance of my sample means. Okay. So this is just kind of variance of my sample means or standard deviation of my sample means, and kind of situations where either I know the population variance or I only have the sample variance. Now notice not a whole lot changes there, right? It's just notation, but these would be the equations that remind us of that. Here's my variances, here's standard deviations, which is simply the square root of those variances, right? Okay, so we'll clear these. But then come down here, right? This was kind of the variance and standard deviation for my sample proportions. We don't have a lot of problems where we're really dealing with this, but this was kind of an intermediate step before we started talking about things like test statistics, right? So then I would then come up here, these equations at the top, right? These are going to be z-scores for either sample means or sample proportions when we know the population mean and proportion, right? So this was going to be kind of stuff that we did before hypothesis testing. So where we knew what the population mean or the population proportion were, and we were just wanting to turn different values for our sample means into z-scores. Okay? So where would this kind of apply on the problems that we were looking at? On practice exam or A or B. This was once we took a sample and started thinking about, okay, what's the probability that my sample mean is, less than 25 or between, sorry, not less than 25, less than 3,550 or between 3,500 and 3,700, right? So the next set of equations we have here are going to be our confidence intervals, right? So these are going to be, you can almost think about it as, here we go. So here's my confidence interval equations are going to be these three right here. Right? So this is with sample mean with a known population standard deviation. Right? This is going to be sample proportion, right, example. And then finally, sample mean with only kind of a sample variance or a sample standard deviation, right? If I know one of those two, if I know the sample variance, well, the sample standard deviation is just the square root of that. So I can be given, either the variance or the standard deviation, kind of depends, right? That's those three different types of confidence interval equations that we could be looking at, okay? So I'll give you a second. I'm just kind of writing those in before I kind of move down, since I can't scroll with these up here, okay? All right. Okay, so I'm going to clear this out. If I went too fast, make sure you ask. Feel free to ask, and I can kind of show you what they are again. So here at the bottom, these three equations, these are going to be our test statistic equations, right? So these are over here. These are our different test statistics. Now remember, if a test statistic comes from a standard normal distribution, it's a Z statistic. If it comes from a student T, it's a T statistic. So the test statistic equations kind of remind us which types of examples we need to be using the standard normal or the Z tables and which ones we need to use the student T. So the only time we use the student T distribution for a test statistic is if we're looking at a sample mean and we only have the sample variance or the sample standard deviation. Anytime in a problem we see the word sample variance or sample standard deviation, automatically we should be thinking about this test statistic here, because sample variance or sample standard deviation, S squared or S, that reminds us it's coming from a student T distribution. Or if we remember that anytime we see the words sample variance or sample standard deviations, we will have a T statistic, right? Because it's going to be coming from a student T distribution. That would also help us kind of identify this is our test statistic that we need to be using. Up here, if we have a sample mean and we know population variance or standard deviation, I'm going to put this down here. If we know the population variance or standard deviation, we know that it's going to be the same kind of formula, but we have a population variance, so we use that standard normal or those Z tables. And then anytime we see the word proportion, whether or not it's a test statistic or a confidence interval, we should be thinking about we're using that standard normal distribution. So if we're looking at a sample proportion and wanting to find a test statistic, this is going to be the equation we use here, okay? So hopefully that gives us a pretty good layout, a pretty good guide to kind of this formula sheet. I mentioned kind of prior to doing this, something else that I would kind of add or write in onto this formula sheet, which was this guy right here, kind of reminding us how we find critical values. Also, I mentioned it, but if we come down here, this kind of table is just a reminder of how you use the alternative hypothesis to identify the type of test. And right, here's where I mentioned you could also think about, this greater than is a right tail, right? So we could kind of do that. Then right down in here, this is a left tail and then a two tail. Right? Also, it kind of reminds us that when we're finding the p-value, you're looking for the area in that right tail for a right tail test, area in the left tail for a left tail test, and then for a two tail test, you can find the area in one tail. Oops, I did not want to do that. Here. Let's clear this real quick. But once you find that area in one tail for a two-tailed test, you need to multiply it by 2 to get your total p-value. Okay, so this is kind of the column for our p-value. Right? Any other questions or kind of generalized questions before maybe I kind of pick a few problems to work through? Okay. All right, I'll try to keep an eye on the chat in case people think of things. So, we worked through a lot of practice exam B. All right, I then mentioned that my other section, we went through practice exam A. If you wanted to see some of that, you could go to the YouTube page. So I'll just kind of remind you where that is. So I'm just going to even search it as though I don't know I don't have the link from the syllabus or anything. So Professor Landis, why? Because I can't spell. There we go. Right, I'll go to my playlists. Even if I look at kind of the playlist for this section, you'll kind of notice there's some section 3 recordings, and that's because this was all just different problems that I had worked through for the practice exam for section 5. So kind of section 3s from today is up there. We did, some of the stuff that we had already done, so that might not be as useful, but section 3's recordings from last week, so the 6th and the 4th, those were essentially, if we click on those, whoops, they'll kind of have, tell me what part of practice exam A those videos went over. I look like very tired in this still, so that's great. So one that we didn't, I don't think he's kind of in those, might, that we covered a little bit today in that section, but I'll kind of go through the same here with you, is let's say we do practice exam A and we look at question 15, okay? So we find kind of this average salary of 145,000. We've got currently a sample size of 30 and a sample standard deviation of 10,000. Let's see what the question is here. Who benefit from our online quizzes? What should people who didn't do well in the Excel stuff last time focus on? So what would I focus on? I would, the first place to start, and yeah, maybe this is more general, just better discussion. The first, because me going through these problems, the video is already out there on how I worked through these problems. So maybe some more advice or just general discussion is warranted. So I would first go through the practice exams, right? A and B. You have me, literally there's videos of me working through every single problem up there on YouTube. So if you get stuck on one or you can't quite get the answer, and you have the answer keys as well, but if there's ones that you can't quite get, you can kind of see how I work through it. If you're still a little bit, stuck, reach out to me. But once you feel comfortable with those practice exams, I would go back through, probably review the online quiz questions, like try to make sure you could like reproduce the answers for those. I think that would be maybe the next best place to start. Then from there, I would try to make sure, you could even put this as number 1, but what we just worked through with the formula sheet, make sure you understand that formula sheet, which formulas kind of stand for what, kind of have anything that I've mentioned, like I did today, something like things written down going into the exam that might be good things to remember. And then after that, do the online quizzes, and then I would, you could go back through and look at the Connect questions. Those are definitely going to be, especially some of them, a little bit more in depth or a little bit more detailed than what you'll see on the exam. But those would be some, more good problems to be able to work through. There isn't anything specific to Excel on these exams. So going over the Excel assignment, although the principles will be helpful, right? And if you want to use Excel to find things like the p-value or to find your confidence intervals, that's great. But, you don't have to use Excel there. So I would kind of rank that as pretty low down where I would start because, if you're not comfortable with it, you don't have to have a great understanding of Excel. You can do all of this by hand, right? And that's really kind of what I've shown you here. And if you are comfortable with Excel and you remember the functions you can use that kind of simulate using the table, then that's okay as well. But that would be, I'd put that one kind of down the list in terms of reviewing the Excel assignment. Hopefully that kind of helped answer. I don't know if I forgot anything else that you might want to go through, but if you want to go through the lecture slides, you could. If you went through the lecture slides, what I would focus on, or anytime there's an example, right? So confidence interval, example number 2. Make sure you understand how to go through all those hypothesis tests, unknown standard deviation example, go through those. So looking at, the example kind of problems will also give you some more to work through if you're kind of looking for additional things, which would be on kind of going through those lecture slides, okay? Okay, any other questions before I kind of jump back into this specific problem here? Okay with that? All right, so let's say I wanted to find the 90% confidence interval for the true mean salary, right? Well, first of all, just, this is for the next 6 questions. So let me just figure out what distribution I'm going to be using for those 6 questions. I've got a sample mean or average salary of 145,000. All I have is this sample standard deviation. So right away, all I have is a sample standard deviation. If I kind of look at the formula sheet, or maybe I had this written down ahead of time, if I only have a sample variance or a sample standard deviation, I'm using the student t, right? The confidence interval and the test statistic equation remind me, if I only have a sample variance or a sample standard deviation, I need to be using that student t distribution, okay? So if I'm looking for a confidence interval for a sample mean with only having a sample standard deviation, which this is what I have here, I need to use that student t distribution. So I have a sample mean of 145,000, I can plug that in. Sample variance, wasn't given the sample variance, all I had was the sample standard deviation. So all I have essentially is S. So when I go to that formula sheet, I put 10,000 here, I still need to square it, right? 10,000 squared. I then divide by 30 was my sample size. The only thing left I have to do is find this student t distribution value, right? So I need to find it for my degrees of freedom, which my degrees of freedom here was, well, my sample size was 30, so my degrees of freedom is n minus 1, so 30 minus 1 is 29, right? I'm going to be building my confidence interval around whatever the sample mean I found was, which I think was 145K. I want to find my upper bound and my lower bound such that the probability that I kind of see something outside this interval is alpha over 2. Well, what's my alpha? Let's go back here. The 90% confidence interval, so alpha is the area outside my interval in decimal form. So 10% is outside of the interval, so 0.1. So 0.1 over 2. There will be 0.05 kind of in each of my tails at degrees of freedom. Where was it? Here, 29, right? So I go to my student t table, right? I say, okay, I wanted 0.05 in my tail at degrees of freedom 29. So 1.699 is going to be the value that I'm plugging into kind of this t value here. Right? Once I have that, add that margin of error to get my upper bound, subtract it to get my lower bound, right? And I should be able to identify which of these is the correct lower and upper bound. So, I could write all this out, but for the sake of kind of being the last time that we're going to be looking through things, I want to go through more problems. So just as you want to see what that looks like, I kind of, showed you with the mouse where you plug everything in at. Oh, that's not the right problem. Here we go. So if you were to plug in all the values and write it out, it would look something like this, right? So kind of remember to square that 10,000, and when we get this as our confidence interval, all right? If we then wanted to say that there's a news publication that says, the average dental salary is 150,000, and I want to test for whether or not the true salary is less than that amount. So whenever you have a problem like this, whatever you want to test for, right, that is your alternative hypothesis. So here what I'm wanting to test for, what I'm trying to find is the true salary less than this reported 150,000? So my alternative hypothesis is it less than 150,000? Once I have identified that alternative, my null is just the exact opposite or the complement of that. So if I want to find that the mean is less than that 150,000 that was reported, I assume that it's greater than or equal to 150,000. So what type of tailed test would I have here? Well, even if we wanted to use that formula sheet, or if we forget, kind of a reminder is, if I see a less than sign in my alternative hypothesis, I have a less than, or I said we could have written in here also a left-tailed test. So I know that for a left-tailed test, right, I'm going to have, and I erase it on the board, but we had already kind of went through this discussion in the class, left-tailed, negative critical values. So right away, I know A or C is going to be the right answer. So if I have a left-tailed test, I could actually just look up the kind of very first alpha. So 0.1, right? 10% significance level is an alpha of 0.1. What I'm thinking about there is I want, excuse me, we're dealing with that student t distribution. So I want the critical value that gives me 0.1 in that lower left tail at degrees of freedom of 29. Now I know that this distribution is centered at 0, so I know that critical value will be negative, right? And my alpha got turned over here, so right, it gives me alpha in the tail. So what do? I go to my student t table. I can look up that very first one, the alpha of 0.1. Come up here. 0.1 is the area I want in the lower left tail. So that's one of the issues with this student t distribution table, right? It always looks at the right side of the distribution. Well, remember, we had a left-tailed test. I wanted the left side. Well, it would essentially be all these same values. It's just that our t values would, instead of being positive, they'd be on the other side of 0, so negative. All right, so I want 0.1 in that lower left tail at degrees of freedom of 29. The critical value that would give me that is negative 1.311. And kind of the key there is knowing that it's negative is because it's a left-tailed test. All right? So I go back here, negative 1.311. Now I could look up the other two values as well, right? But once I see that negative 1.311 is the critical value at the 10% level, I automatically know kind of the other two. I mean, I can identify from this multiple choice problem what the other two would be. Now, I could have at degrees of freedom of 29 said, okay, well, what if my alpha was 0.05 or 0.01? Scroll down here and use those columns. Negative 1.699 and negative 2.42. That's how we would get those other two critical values, okay? So what if I wanted to find the test statistic for this test, right? Well, I look at my formula sheet. My test statistic equations we identified earlier were right here. I have a scenario where I know the sample mean, but I only have a sample standard deviation or a sample variance. So I'm going to be using a student t distribution, or the test statistic equation that kind of fits my scenario is this guy right here. So I've got my sample mean of 145,000. I've got that assumed true mean, which we said we were assuming was 150,000, right? Or kind of greater than or less than 150,000. The standard deviation was 10,000. Sample size was 30. So we plug all those values in. Once we do that, right, we just plug those values in. We'll get something that looks like this. Now, I mean, at this point, once I help you identify the correct formula, really this part is just a matter of being able to plug the values in and use your calculator correctly. But one thing that can kind of prevent you from making some easy mistakes is look at your null and alternative hypothesis. Here, we assumed that the true value that these sample means would be distributed around, which was the assumed true value for the population mean, was 150,000. We found sample evidence of 145,000. So when I turn this into a student t distribution, or into my test statistics, that student t distribution, when I think about this assumed true mean, it'll always have a test statistic. If I was to turn my assumed true mean into a test statistic, it would always be 0. So anytime I see sample evidence below what I assume to be true, I know that my test statistic is going to be negative. If I see anything that's above the assumed true mean, my test statistic will be positive. So here, I know my test statistic will be negative. So when I go to those possible answers, no, that's the answer key. I can rule out C and D right away because I know my test statistic has to be negative. Now, if I'm just guessing at this point, I'm probably going to guess A is the correct answer because B would mean that the sample evidence I found was 274 standard deviations away from the assumed true value. Now, look, if a standard deviation was low enough, yes, it would be possible, but we found a sample mean of 145,000. It's not that far away from 150,000. I mean, we would need a pretty small standard deviation to be, for 5,000 to be, 274 standard deviations away. But, you know, we could plug everything into our equation to make sure that, you know, we actually get the correct value in case there was some other answers that made more sense. And if we do that, we'll get negative 2.74, okay? All right, now on 19, right, I kind of give you this explanation in the answer key that I'll kind of walk through, and I think maybe show you an easier way to do this on the exam, right? Let's assume the test statistic you found was negative 1.5. What levels could you reject the null hypothesis at? Well, it's kind of hard to use the p-value approach with a student t-distribution. So let's assume first that, let's just do the critical value approach, and then I'll show you what it would look like if you wanted to use the p-value approach. So here's my critical values. We already had them, right? So negative 1.311, we'll just plot those. Right? So I'm going to plot these critical values. So what was it? Negative 1.311, negative 1.699, and like negative 2.46, I think. Remember, define your rejection regions. That's just kind of anything that's larger in absolute value than your critical values, or kind of draw those arrows in the tail. I think the assumed true test statistic that you were given was 1.5. So let me make sure you double check that, but I think that's what the problem said. Yeah, assume that the test statistic that we found was 1.5, right? So if I plot that, it's going to be right here. So it's in the rejection region at the 10% level. So I rejected the 10% level. It's not quite in the region at the 5% level. So I, failed to reject at the 5% level. And it's definitely not in my rejection region at the 1% level. So I failed to reject at the 1. So the only level I can reject here is the 10% level because my test statistic is only in the rejection region for that 10% level, or an alpha of 0.1. Okay? Now, if I wanted to find the p-value approach, right, what I would have done was I was really looking for the probability I saw something this far away from the assumed true value or anything further. So I turn this into a test statistic, and then I'm essentially looking for the area in a left-tailed test, the area to the left of it. Right? Well, I know my degrees of freedom we had earlier was 29. I now want to look up my test statistic in the student t-table and find the probability I saw something that was that far away or anything further, right? Or the kind of area in that left tail. So I go to my student t-table. Now the problem here is that degrees of freedom of 29. Well, first of all, we have to remember we're doing the left side of the distribution, so really we should think of these all being negative. I had a test statistic of negative 1.5, so where would that fall in between? Negative 1.3 and negative 1.69. So my test statistic isn't a number in this table, but I know it would be in between these two test statistics. So I go up. The area to the left of negative 1.31 would be 0.1. The area to the left of, 1.699, the area to the left of that is 0.05. So my p-value, since my test statistic was in between the test statistics that would give me these two areas, my p-value will be somewhere in this range, somewhere in between 0.05 and 0.1, right? So all I can do with that student t-distribution is say that my p-value is somewhere in between 0.05 and 0.1. Okay? Now, if I'm trying to make my rejection decision, probably the easiest way to do this, right, is if I remember I only reject if the p-value is less than alpha, right? So here's my different kind of alpha levels. Instead of trying to think about this range, choose a p-value that would fit the bounds that you put on it. So what's a value that's in between 0.1 and 0.05? 0.075. Now it makes that check a little bit easier because now I can just say, okay, is 0.75 less than 0.1? Sure enough it is, I can reject. Is 0.05 kind of less than 0.05? No, it's not. I fail to reject. Well, if it's not less than 0.05, it's definitely not less than 0.01. So I only reject at that 10% significance level, not at the other two, which is the same decision that we made using the critical value approach, right? But it was a little bit harder because I could only kind of put that bound on my p-value, okay? Any questions on that? Stay out of the way here if people are writing this down. Minus an alpha. Okay. So I think the question that was asked is related kind of to p-values. So let's assume that we had a two-tailed test here. Once we found the area here, it would have been equally as likely for us to have found sample evidence on this side. And so really we had two tails of the same value. So now with a two-tailed test, once I find this area, I've only got half my p-value. So I need to multiply it by 2 because I have another tail on the other side that's equally as large, right? So I find the area in one tail and I multiply it by 2. So why, when I'm looking at my critical value, do I divide alpha by 2? Well, because what I'm doing with my critical values is I want alpha total in the tail. So because before I don't know the area in the tail, I'm looking for the area in the tail. Once I find the area in one tail, I have to multiply it by 2 to get the total area in the tails. But when I start out knowing the total areas I want in the tail, well then I know that alpha is kind of split up between the two. So when I start out knowing alpha, I have to divide it by 2, right? Because alpha total is the area of the tails, so to know the area that's in one tail, I have to divide alpha by 2. If I'm trying to find the area in the tails, like I don't know it, right? Here I started out knowing it. Well, now when I find the area in one tail, I know that the total area kind of in both my tails would be whatever this is times 2. Kind of like here, if I told you, let's say I told you the area in the tail, I gave you the critical value, you look up the area in one tail and it's 0.05. Well, that would tell you that alpha, right? If you know that the area in one tail is 0.05, then to know what alpha is, you would have to multiply that by 2. So it's not so much that it's anything kind of different, just that when we're dealing with alpha, we always start out knowing alpha, and then we're trying to find kind of the critical value that gives us alpha total in the tails, so half of alpha is in each tail. Here, we start out knowing kind of this value, right? We start out knowing the test statistic, the z or the t value. We then look up the area in one tail, and because we want the total area in both, that's what we have to multiply by 2. It's almost like we're coming at it from like 2 different directions. Excuse me. Hopefully that kind of answered your question. Any other questions? Okay. So we kind of looked up that p-value. The next thing, so this question 20. Let's say instead of 30 dentists, we had found 60. Which of the following is going to be true? Well, we can try to analyze each one of these, but I'm just going to kind of walk through in general. You know, we could actually say a lot of things, right? So we took a higher sample size, right? So to understand kind of what's going on with the math, and then also visually, let's say we have our test statistical equation here. Where the denominator represents the standard deviation of our sample mean. So let's start out assuming, right, that we had found, so here was our, what was the value? 145,000. And this would have been kind of our p-value with a sample size of 30. Let's assume now we take a higher sample size, which is 60. Now we could prove this to ourselves. We've had all the numbers. We could just rework it and figure out what our new test statistic would be. But if we think about mathematically, what's going to happen is if my sample size goes up, what happens to this fraction right here? Well, it's going to go down because I'm dividing by a larger number. So my denominator here is going to get smaller, right? It's the denominator of my test statistic, which if it represents the standard deviation of my sample means, I'm going to have a smaller standard deviation of my sample means, which means the distribution gets more peaked. Now finding that same sample evidence, my p-value is a smaller area, right? So we kind of see here already that my p-value is going to go down if I take a higher sample size and I find the same sample mean. Well, now notice that this denominator was smaller. What happens to my test statistic? Well, a smaller denominator means I'm dividing by a smaller number. The whole kind of fraction goes up. Well, if the whole fraction goes up, really what this is saying is that before, here was kind of my test statistic, and the p-value would have been the area to the left. Now, here's my new test statistic, right? When I say it goes up, it's larger in absolute value. So I gotta be careful there. When I say it's increased, it's increased in absolute value, right? Because it's become a larger negative value, right? I'm dealing with a left-tailed test here. So now you can kind of see the p-value, or the area to the left of that test statistic, just like when I drew it up here, is now smaller, right? So my test statistic goes up when I have a higher sample size. My p-value would then go down, right? So if my p-value gets smaller, and I only reject when the p-value is less than alpha, well, if this p-value is getting smaller, then it's going to be more likely that it is less than alpha, or I'll be more likely to reject, right? So just from taking a higher sample size, if we saw everything else stay the same, I know that I'll end up with a higher test statistic, or a greater in absolute value test statistic. My p-value will get smaller, because now the probability that I saw 145,000, if the true mean of 150,000 was in fact true, it's going to be less likely because the standard deviation is decreasing in my distribution. And with a smaller p-value, I know it's going to be more likely that the p-value is less than alpha, or I'm going to be more likely to reject, right? So if we looked at kind of the options there, the new test statistic will be smaller. Well, here, like I said, on the exam, I'll be kind of use a little more pointed language, which would be it's smaller in absolute value. It's not going to be. We took a higher sample, so we know the test statistic will be larger in absolute value. The new p-value will be larger than before. What we said, it'll be actually be smaller. And because it was smaller, what we said was going to be true was it would be more likely to reject. So C is going to be our correct answer there. Okay. Any questions on that, or any other kind of questions here? Okay. One thing that problem 21 deals with that I just want to make sure I kind of reiterate. So it gives you an example, like, should you use a student T or standard normal? Wait, what does this say? Hold on. Oh, for the kind of, sorry, I didn't even see this. Probably should have. There we go. Right? So we have this proportion example. Right away, anytime we see proportion, so this is when I want to kind of clarify this a little bit too. So let's say any type of confidence interval or test statistical equation that you have, anytime you see this word proportion, or like we see that we're dealing with a sample proportion, automatically we should know we're using the standard normal or the z-tables. The only other time we use the z-tables is if we have a sample mean and we have a known kind of population standard deviation or a population variance, or we know sigma squared, we're also using the z-table there. The only time we use a student t-table is if I have a sample mean and all I have is either the sample variance or the sample standard deviation, or another way of saying this, I have an unknown population standard deviation. This is the only time I use that student t distribution. So in the problem that we're given at 21, it starts talking about proportions. Anytime you see the word proportion, automatically you know you're dealing with a standard normal table, right? So we should be using the standard normal because we're creating a test statistic for a sample proportion, right? That, you know, once we know we're dealing with proportions, we always know we can use that standard normal distribution for confidence intervals and test statistics. Okay? All right. Any other questions kind of about the exam or some specific, kind of maybe a specific problem? Probably not going to have time to go through like a group of questions here. We've only got 5 minutes left. But maybe one specific problem or why something in the answer key, you know, looks the way it does. No more questions? I do these exam reviews. You know, you guys have specific ones. You can kind of go through those. One thing I want to mention, just to kind of reiterate, for those of you, I looked earlier, no one had kind of started or taken the exam yet. Make sure, and I might have said this at the beginning, but I'm going to kind of hammer it down even more. Upload whatever work you do for that short answer question in Word, Excel, or your picture of your work for that short answer, that last question. Because if you just give me a wrong answer, I need to make sure that I can give you as much partial credit as possible. If you just give me like, negative 1.3 is the test statistic. Well, if I can't see any of your work and it's just wrong, I can't give you any partial credit. So make sure you upload all, show all of your work so that if you do get it wrong for some reason, I can give you as much partial credit there as possible, right? Do we go through number 8 already? So number 8, I went through one similar on practice exam B in class last week. There is video of me doing that on YouTube for my other section, but kind of I can walk through here pretty quick as we end here. So start out kind of having this calorie consumption for U.S. citizen, a mean of 3,700. You are also given kind of the variance. So this is one where we haven't taken a sample yet. This is just the original normally distributed variable. We know it's mean, we know it's population variance. In 8, right, we say what's the probability that if we sampled 25 people that we see a sample mean less than 3,550. Right? So what we're thinking about there is anytime we look at sample means, we know they should be normally distributed around whatever the true population mean was. Now with hypothesis testing, we had to use assumed true means because we didn't know it. Well, this is a scenario where we know that the population mean, the variable we were sampling from, the population mean was 3,700. We found 3,550 as our sample mean. So what's the probability that we saw that or anything less, right, is going to be this area, right? I want to make sure that's actually what the question asked. I think it was less than. Yeah, less than that 3,550. So we're going to, because we know the population mean, right, and we were given the population variance, we're going to turn this into a z-score, look that up in the table and find the area to the left. Now right away, we know that area has to be less than 0.5 because the area to the left and the right of the mean would be 0.5. So we want something much smaller than that. So how do I get this test statistic, or not test statistic, how do I get the z-value for a sample mean? Well, if we look at our formula sheet, go up here. This is when we get the test statistic for a sample mean when we have this like known population mean, right? So I take 3,550 minus 3,700, plug in my variance and my sample size, and that should give me my z-value there. I think, if I remember right, let's look at this because I'm not sure I'm going to do this right in my head. So plug all those values in. Yeah, so we have about negative 1.5, right? So this value here was negative 1.5. I'll look that up in my z-table. It'll give me the area to the left, which is what I wanted. If I can get my screen to share again. What's going on? There we go. So I go to my z-table, which I didn't have pulled up here. I look up negative 1.50, so 0.0668. That's the area to the left. I wanted the area to the left, so I don't have any more work to do. So my answer here would be A, right? What's the only thing that would change if I wanted the probability that I saw greater than 3,550? Well, then I would want the area to the right, so I would take that 0.0668, subtract it from 1. Right? That's another type of problem I could maybe ask you. Okay. All right. Any last kind of minute questions here? Probably end the video. If you do have some kind of last minute questions you want to ask after I end this, I'll kind of leave Zoom up for a little bit. Other than that, good luck on the exam. Remember, try not to use Safari as your browser. Try to use Chrome, Firefox, or Internet Explorer. If you have any questions kind of before you take the exam, feel free to reach out to me. I'll be pretty available today and tomorrow if you wanted to set up a time to meet, either in person or via Zoom. All right? All right, I'll see you guys on Wednesday.